Moving on to Chapter 14, this covers turbo machinery. And while this chapter is split primarily into pumps and turbines, we will be focusing on going in depth with the pumps only, not so much the turbines. It's okay if you see terminology coming forward like turbo machinery and defining things like turbines and such in those references. Just know that when we are going in depth, we will only be doing so primarily into pumps. So here is a jet engine on a modern commercial airplane, and they're highly complex turbo machines that include both pump, compressor, and turbine sections. Here's our objectives, classifications, and terminology. So a pump, which is what we are going to be focusing on, is energy absorbing devices, since energy is supplied to them, and they transfer most of that energy to the fluid, usually via a rotating shaft. In work, the increase in fluid energy is usually felt as an increase in the pressure of the fluid. And then turbines, while we're not going to go into it, it is good to define. Turbines are energy producing devices, so just the opposite. Pumps consume, turbines produce. Energy producing devices that they extract energy from the fluid and transfer most of that energy to some form of mechanical energy output. Okay. So what is the purpose of a pump? The purpose of a pump is to add energy to a fluid, resulting in an increase in fluid pressure, not necessarily an increase in fluid speed across a pump. Okay. And so you can see this pump and the increase in velocity that it would experience due to its converging. What is the purpose of a turbine? It's to extract energy from a fluid, resulting in a decrease of the fluid pressure, not necessarily a decrease in fluid speeds across a turbine. So pump, again, fluid machines that move liquids. Fan is a gas pump with relatively low pressure rise and high flow rate. Examples include ceiling fans, house fans, propellers, things like that. A blower is a gas pump with relatively moderate to high pressure rise and moderate to low flow rate. Examples include centrifugal blowers, which we will, where's my pen? Why is it not? Oh, hang on. It is not. Is it taking into account? There it is. Sorry about that. Okay. This we will be focusing on later. In squirrel cage blowers and automobile ventilation system, furnaces and leaf blowers. And then compressor is a gas pump designed to deliver a very high pressure rise, typically at low to moderate flow rates. Examples include air compressors that run pneumatic tools and inflate tires at automobile stations, refrigerant compressors used in heat pumps, refrigerators, air conditioners, things like that. And so here is just a diagram. If you have a change in pressure that is low, that could be a fan, medium could be a blower, high could be a compressor. And then if you have a volume rate here, if you have a high volume rate, you've got a fan, medium volume rate, you've got blower, and low volume rate, you've got a compressor. Here, when we use with gases, pumps are called fans, blowers, or compressors, depending on the relative values of pressure rise and volume flow rate. Turbo machines, what do we mean when we say turbo machines? Pumps and turbines in which energy is supplied or extracted by a rotating shaft. The word turbo machine and turbo machinery are often used in the literature to refer to all types of pumps and turbines, regardless of whether they utilize a rotating shaft or not. So it's just an all-encompassing terminology. Fluid machines may also be broadly classified as either positive displacement machines or dynamic machines, based on the manner in which they transfer energy. In positive displacement machines, fluid is directed in a closed volume. Energy transfer to the fluid is accomplished by movement of a boundary of a closed volume, causing the volume to expand or contract. Think of a piston, thereby sucking fluid in or squeezing fluid out, respectively. So here we've been covering the cardiovascular system. The human heart is an example of positive displacement pump. Blood is pumped by expansion and contraction of heart chambers, called ventricles. And then B here, the common water meter in your house is an example of positive displacement turbine. Water fills and exits a chamber of known volume for each revolution of the output shaft. Dynamic machines. There's no closed volume. Instead, rotating blades supply or extract energy to or from the fluid. So you can see this windmill. There is no closed volume, right? It's interacting with the atmosphere. It's interacting with its surroundings. Whereas over here, this human heart is definitely a closed volume. This water meter is definitely a closed volume. Nothing's leaving. The fluid is going through the pipes per se, right, through the veins. And here it's going maybe through an inlet, right, or vice versa. For pumps, these rotating blades are called impeller blades, while for turbines, the rotating blades are called runner blades or buckets. Examples of dynamic pumps include enclosed pumps, induct pumps, and open pumps. Examples of dynamic turbines include enclosed turbines such as hydroturbine that extracts energy from water into the hydroelectric dam, and open turbines such as the wind turbine that extracts energy from the wind. Pumps. The mass flow rate of fluid through the pump is an obvious primary pump performance parameter. We are looking at the mass, hit it again. We are looking at the mass flow rate. For incompressible flow, it is more common to use a volume flow rate rather than a mass flow rate. And in turbomachinery, volume flow rate is called capacity. So we use that with capacity. And is simply mass flow rate divided by fluid density. So it's just taken into account that density here at rho. The performance of a pump is characterized additionally by its net head, H, defined as the change in the Bernoulli head between the inlet and outlet of the pump. And you see that here, the difference between out versus in. And that is the net head, net. For a case in which a liquid is being pumped, the Bernoulli head at the inlet is equivalent to the energy grade line at the inlet. So you see that here. And then you have special cases for water horsepower, brake horsepower, and pump efficiency, of course. The net head of a pump, H, is defined as the change of the Bernoulli head from the inlet to the outlet. We just talked about that. For a liquid, this is equivalent to the change in the energy grade line. Here we see that. Relative to some arbitrary datum plane. BHP is the brake horsepower, the external power supplied to the pump. And you see this datum plane down here. Pump performance curves matching a pump to a piping system. So it's incredibly important for you to choose the correct pump for each piping system. Free delivery, the maximum flow rate through a pump occurs when its net head is 0, H equals 0. The flow rate is called the pump's free delivery. So it's what it is able to achieve. Shutoff head, the net head that occurs when the volume rate is 0 and is achieved when the outlet port of a pump is blocked off, right? Shut off, blocked off. Under these conditions, head is large, but V is 0. And the pump's efficiency is again 0 because the pump is doing no useful work. And of course, anytime we have any rates, we have efficiency, and so we have the best efficiency point, BEP. The pump's efficiency reaches its maximum value somewhere between the shutoff condition and the free delivery condition, right? So it's obviously not going to be 0 because that's where there is no efficiency. And then it's not just going to be free delivery as well. Pump performance curves, so it's the curves of H in the efficiency, and BHP as functions of the volume flow rate. And they may also be called the characteristic curves. And then the operating point or duty point of the system. In a typical application, the H required and H available match at one unique value of flow rate, and this is the operating point or the duty point of the system. That's what you want to reach. For steady conditions, a pump can operate only along its performance curve. And the steady operating point of a piping system is established at the volume flow rate, where H required equals H available. And so you see that here. So you have a typical pump performance curves for the centrifugal pump with backwards incline blades, and the curve shapes of other types of pumps may differ, and the curves change as shaft rotation speed up. Okay, and so here you have this best efficiency point, so it can either be H asterisk, BHP asterisk, etc., things like that. It's just notated by an asterisk. So that's the best efficiency point. So you see you have these efficiency points. So this is line H, but this with an asterisk, that's the most efficiency. And here as well, right? So all of these along this line, and this is the BEP. So anything along this BEP where it crosses, you're going to get that efficiency there. Here, shut off head, because this is 0% efficient, right? And then free delivery is also not going to be the best case scenario. But it is the highest mass flow rate for sure. Operating point of a piping system is established as a volume flow rate where the system curve and the pump performance curve intersect. So you want both of those. You want not only the pump performance curve, but you want the system curve here. So you can have more than one operating point, and this should be avoided, and you should just choose a different pump so that you can get a singular definitive operating point. Useful pump head delivered to fluid does 4 things. Number 1, it increases the static pressure of the fluid from 0.1 to 0.2. It increases the dynamic pressure, which is the kinetic energy, of the fluid from 0.1 to 0.2. It raises the elevation, which is the potential energy of the fluid from 0.1 to 0.2. And lastly, it overcomes irreversible head loss in a piping system. And then here, above equation emphasizes the role of a pump in a piping system, namely it increases or decreases the static pressure, dynamic pressure, and elevation of the fluid as it overcomes irreversible losses. And this is just depending on what you need to pump. So just depending on if you need it to be increased or decreased. Here's an example, an operating point of a fan in a ventilation system. And here it is on a XY axis. Net head as a function of the volume flow rate for a ventilation system of the previous example. The point at the available required values of H intersect the operating point. So you can see that here. So here it states that it's common practice in pump industry to offer several choices of impeller diameter for a single pump casing. And there are several reasons to do this. And first and foremost, to save manufacturing cost. It enables capacity increase by simple impeller replacement, to standardize installation mountings, and to enable reuse of equipment for a different application, which thus reduces cost. Here is a very detailed performance plot for a family of centrifugal pumps. Each pump has the same casing, but a different impeller diameter. So here in some applications, a less efficient pump from the same family of pumps may require less energy to operate. An even better choice, however, would be a pump whose best efficiency point occurs at the required operating point of the pump. But such a pump is not always commercially available. And so here it has a little splurt up here. Is she trying to tell me that a less efficient pump can actually save on energy costs? Absolutely, because picking a pump is not always about what is most efficient or XYZ. It's about matching it. It's about the relationship to the setup and the goals that you have. Pump cavitation and net positive suction head. When pumping liquids, it is possible for the local pressure inside the pump to fall below the vapor pressure of the liquid, which is PV. And when that pressure does fall below PV, vapor-filled bubbles called cavitation bubbles appear. The liquid boils locally, typically on the suction side of the rotating impeller blades, where the pressure is lowest. Net positive suction head is the difference between the pump's inlet stagnation pressure head and the vapor pressure head. And here is the formula for that. So you do have a required net positive suction head. It's the minimum net positive suction head necessary to avoid cavitation in the pump. So it's what you have to avoid that cavitation. Here's an example. It's the maximum flow rate to avoid the cavitation, the pump cavitation. So net positive suction head as a function of the volume flow rate for a pump. At 2 temperatures, the cavitation is predicted to occur at flow rates greater than the point where the available and required values of the net positive suction head intersect. So here, if we need to increase volume flow rate or pressure by just a small amount, we can add an additional pump or a smaller pump, and we can do so by a series. So that's one after another. So first it would be 1, then moving on to another it would be 2. Or you can do a parallel. So that's going in, and then you would have flows going in, and then both exiting in parallel. So combined net head for any number of pumps in a series, and that's just the sum of those. So just combining them. So here you can see a pump performance curve. It's the dark blue in a series at low values of flow rate. Volume flow rate, the combined net head is equal to the sum of the net head of each pump by itself. So you just add them together. That's what the combine is. You literally take them, combine them, and add them together. Okay? However, to avoid pump damage and loss of combined net head, any individual pump should be shut off and bypassed at flow rates larger than the pump's free delivery, as indicated by the vertical dashes and the red lines. If the 3 pumps were identical, it would not be necessary to turn off any of the pumps, since the free delivery of each pump would occur at the same volume flow rate. We do have a combined capacity for any number of pumps as well in parallel. So that's here in just the sum of those. So pump performance curve, again, the dark blue. For the 3 pumps in parallel, at a low value of net head, the combined capacity is equal to the sum of the capacity of each pump by itself. So just the same, you just combine them, you add them together. However, again, to avoid pump damage, the loss of combined capacity, any individual pump should be shut off at net heads larger than the pump's shut-off head, as indicated by the horizontal dashed lines. That pump's branch should also be blocked with the valve to avoid reverse flow, backflow. If the 3 pumps were identical, it would not be necessary to do so. Here's several identical pumps. They're often run in parallel configurations so that a large volume flow rate can be achieved. When necessary, these 3 parallel pumps are shown. So positive displacement pump, we talked a little bit about that in regard to the cardiovascular system. Fluid is sucked in an expanding volume and then pushed out along as the volume contracts, but the mechanism that causes this change in volume differs greatly among various designs, right? It's going to differ among one pump versus your heart, right? But overall, still doing the same thing, sucking in and then pushing out, right? Positive displacement pumps are ideal for high pressure applications like pumping viscous liquids or thick slurries, and for applications where precise amounts of liquid are to be dispensed or metered, as in medical applications. So here's a 4-phase, 1/8 of a turn apart in the operation of a 2-lobe rotary pump, a type of positive displacement pump. The light blue region represents a chunk of fluid pushed through the top rotor. So it's going in. So this is what we're looking at. So it's going in, and then it's going up and around and around and around, right? While this orange is going the opposite direction. Comparison of a pump performance curves on a rotary pump operating at the same speed, but with fluids of various viscosities. To avoid motor overload, the pump should not be operated in the shaded region. So positive displacement pumps have many advantages over dynamic pumps. They can handle shear sensitive liquids, since the induced shear is much less than that of a dynamic pump, operating at a similar pressure and flow rate. An example of that is blood. Blood is a shear sensitive liquid. Dynamic pumps. There are 3 main types of dynamic pumps that involve rotating blades. Impeller blades or rotor blades, which impart momentum to the fluid. They're sometimes called rotodynamic pumps or just simply rotary pumps. Rotary pumps are classified by the manner in which the flow exits the pump. So it can either be centrifugal flow, axial flow, or mixed flow. So going over those 3, the centrifugal flow pump, fluid enters axially, which is in the same direction as the axes of the rotating shaft in the center of the pump, but is discharged radially or tangentially along the outer radius of the pump casing. For this reason, centrifugal pumps are also called radial flow pumps. And then going on to axial flow pumps, fluid enters and leaves axially, typically along the outer portion of the pump because of the blockage by the shaft, motor hub, etc. And the mixed flow pump is the intermediate between the two, the centrifugal and the axial, with the flow entering axially, not necessarily in the center, but leaving at some angle between radially and axially. So here moving to centrifugal pumps, and blowers can be easily identified by their snail-shaped casing called a scroll. They are found all around your home, dishwashers, hot tubs, clothes, etc. They're used in cars, the water pump engine, air blower, and they are ubiquitous in industry as well, building ventilations, washing operations, etc. Impeller and rotor. In pump terminology, the rotating assembly that consists of the shaft, the hub, and impeller blades, and the impeller shroud. A shroud is the surrounds of the impeller blades, and it increases the blade stiffness. And then here's a side view and a frontal view of a typical centrifugal pump. So there are 3 types of centrifugal pump based on the impeller blade geometry. You've got a backward incline blade. You can see that here. So you can see this is kind of like a backward incline. Radial blade, so just straight. And then forward incline is the opposite of A. So it's just going to face forward. Centrifugal pumps with backward incline blade, which is A, are the most common. These yield the highest efficiency. So A is the highest efficiency of the 3 fluid flows in and out of the blade passages with the least amount of turning, right? So that would be the highest, right? The radial blades, which is B, often called straight blades, have the simplest geometry to produce the largest pressure rise of the 3. And then the forward incline blades produces a pressure rise that is nearly constant. So here are those three types plotted. So you see A, B, and C. And then D is a comparison of net head and brake horsepower performance curves for the three types. Here's the formulas that are associated with the volume flow rate and a close-up side view of the simplified centrifugal pump, flow pump used in elementary analysis of the velocity vectors. We assume that the flow is everywhere tangent to the blade surface when viewed from a reference frame rotating the blade. So shaft torque is equal to the change in momentum from inlet to outlet and is given by the Euler turbo machine equation. And it's also called the Euler turbine formula or the Euler, depending on the pronunciation. So here's the Euler turbo machine equation, or the alternate form, the Euler turbo machine equation, and then the net head at the bottom. And here's additional formulas, including the Bernoulli equation in rotating reference frame. And again, we will go over these in the video where we are working these. So here's an approximation of flow through the impeller with no irreversible losses, so that ideal look. It is often more convenient to work with the relative frame of reference rotating with the impeller. In that case, the Bernoulli equation gets the additional term as indicated in this equation 1422. And then here is a close-up frontal view of the velocity vectors of an impeller blade inlet. The absolute velocity vector is shown in the bold arrow. Here you can see the centrifugal pump A impeller with too few blades, and it leads to excessive circulatory flow loss. And then B is one with too much, right? So too many blades, that leads to passage losses due to excessive flow blockage and large skin friction drag. So here, while the predicted performance is close to the actual performance, at design conditions, the two curves deviate substantially away from the design conditions. At all volume flow rates, the actual net head is lower than the predicted net head. This is due to the irreversibilities, right? Friction, leakage, the swirl, the flow separation, passage loss, and just dissipation. So then moving on to axial pumps, they do not utilize the so-called centrifugal point forces. Instead, the impeller blades behave more like the wing of an airplane, producing lift by changing the momentum of the fluid as they rotate. The lift force on this blade is caused by the pressure differences between the top and the bottom surfaces of the blade, and the change in flow direction leads to that down wash, which is a column of descending air through the rotor plane. And from a time average perspective, there's a pressure jump across the rotor plane that induces a downward airflow. And so you can see this downwash and pressure rise across the rotor plane of a helicopter, which is a type of an axial flow pump. So here, imagine turning a rotor plane vertically. Now we have a propeller, so it's no coincidence. Both the helicopter rotor and the airplane propeller are examples of open axial flow fans, since there's no duct or casing around the tips of the blades. A well-designed rotor blade or propeller blade has twist, as shown as the blue cross-sectional slices through one of the three blades. And equation 1427 is not exact for several reasons. First, the rotating motion of the rotor introduces some swirl to the airflow. This reduces the effective tangential speed of the blade relative to incoming air. Second, since the hub of the rotor is of finite size, the air accelerates around it, causing the airspeed to increase locally at cross sections of the blade close to the root. And then third, the axis of the rotor or propeller may not be aligned exactly parallel to the incoming air. Finally, the airspeed itself is not easily determined because it turns out that air accelerates as it approaches the whirling rotor. So here's a typical fan performance curves for a propeller, which is the axial flow fan. Unlike centrifugal fans, brake horsepower tends to decrease with flow rate. The efficiency curve leans more to the right compared to that of a centrifugal fan, and the result of the efficiency drops off rapidly for flow rates higher than that at the best efficiency point at that BEP. The net head curve also decreases continuously with flow rate, although there are some wiggles, and its shape is much different than that of a centrifugal flow fan. It's usually best to run a propeller fan at or slightly above its maximum efficiency point. So here, if you have a single impeller axial flow fan, it's called a tube axial fan, and you can see that in the top image. And then if you add a second that rotates in the opposite direction, it's called the counter-rotating axial flow fan. And then an axial flow fan with a set of rotor blades, the impeller or the rotor, and a set of stator blades are called vanes, or stator is called the vane axial fan. So here you have, for axial flow fans, you have A, which is a belt-driven tube axial fan without stator blades, and then B is a direct-driven van axial fan with stator blades to reduce swirl and improve efficiency. Here's just the analysis of those. And typical fan performance curves for vane axial flow fan, and then a multi-stage axial flow pump consisting of 2 or more rotor stator pairs. And then the Pratt & Whitney PW4000 turbofan engine is an example of the multi-stage axial flow turbo machine. So we do have pump scaling laws in a dimensional analysis, and you have these formulas here. And you have the head coefficient, the capacity coefficient, and the power coefficient, and those are all dimensionless pump parameters since it is a ratio. So here you have this efficiency as well, and then pump A and pump B. So dimensional analysis is useful for scaling 2 geometrically similar pumps. If all the dimensionless pump parameters of pump A are equivalent to those of pump B, the 2 pumps are dynamically similar, and this is really important for modeling as well. So when plotted in terms of dimensionless pump parameters, the performance curves of all pumps in a family of geometrically similar pumps collapse onto one set of non-dimensional pump performance curves. Values at the BEP are indicated by asterisks. So here you see that scaled model and then the prototype, and the Moody efficiency correction equation for pumps below. And this is talking about when we're talking about taking a small scaled model to test and predict a full scale prototype. So here we have the pump specific speed, and then pump specific speed in customary US units, and then it in European units as well. Here's the conversion ratios between the two. And then maximum efficiency as a function of pump specified speed for the 3 main types of dynamic pumps. The horizontal scales show those non-dimensional pump specified speed and specified speed in customary US units, and it in European units as well. And then affinity laws. So these equations 14 through 38, A, B, and C, apply to both pumps and turbines. It states that A and B can be any 2 homologous states between any 2 geometrically similar turbo machines, or even between 2 homologous states of the same machine. Examples include changing rotational speed or pumping a different fluid with the same pump. Here's VH&P when the affinity laws are applied to a single pump, in which the only thing that is varied is shaft rotational speed. The speed of the pump is increased, net head increases rapidly, brake horsepower increases even more rapidly. And here's a diagram for the manufacturer's performance data for a water pump operating at 1725 RPMs and the room temperature for that example. The data points are smoothed dimensional pump performance curves for the water pump. And then the affinity laws are manipulated to obtain an expression. Let's end with a short video on centrifugal pumps.
Pumps are the most preferred pumping devices in the hydraulic world. In this video, we will have a conceptual overview of working of centrifugal pumps. At the heart of the system lies the impeller. It has got a series of curved vanes fitted inside shroud plates. The impeller is always immersed in water. When the impeller is made to rotate, it makes the fluid surrounding it also rotate. This imparts centrifugal force to water particles, and the water moves radially out. Since rotational mechanical energy is transferred to the fluid, at discharge sides of impeller, both pressure and kinetic energy of water will rise. At suction side, water is getting displaced, so a negative pressure will be induced at I. Such low pressure helps in sucking fresh water stream into the system again, and this process continues. This is the reason why priming is important for centrifugal pumps. If no water is present initially, the negative pressure developed by rotating air at I of impeller will be negligibly small to suck fresh stream of water. Impeller is fitted inside a casing, so the water moving out will be collected inside it and will move in the same direction of rotation of impeller to the discharge nozzle. Here you can note one specialty of casing. It has got increasing area along the flow direction. Such increasing area will help in accommodating newly added water stream and will also help in reducing exit flow velocity. Reduction in flow velocity will result in increase in static pressure, which is required to overcome resistance of pumping system. Here you can see more details of vanes inside impeller. They are backward curved vanes with state-of-the-art I configuration. This vane is extracted from a Kirloskar pump model. If pressure at suction side of impeller goes below vapor pressure of water, a dangerous phenomenon could happen. Water will start to boil, forming vapor bubbles and spoil impeller materials over time. This phenomenon is known as cavitation. More the suction head, lesser should be the pressure at suction side to lift water. This fact puts a limit to maximum suction head a pump can have. Careful pump selection is required to avoid problem of cavitation. Current impeller type is enclosed. Semi-open and open impellers are also in use depending upon application. If the working fluid is cloggy in nature, it is preferred to use open kind of impeller, but they are slightly less efficient. Mechanical design of centrifugal pump is always challenging. A shaft is used to connect between the impeller and motor. Since water pressure inside casing is huge, a proper sealing arrangement is imperative in arresting water leakage through shaft casing clearance. Mechanical seal or stuffing box-based mechanism is used for this purpose. Impeller is mounted on bearings. But at suction side of impeller, it is not advisable to fit a bearing since it will block the flow. So bearings have to be fitted at the other end. This means impeller is mounted like a cantilever. For high flow rate pumps, a bearing housing with cooling oil is necessary for improving life of bearings.